In Chapter 19, we will be discussing the catalytic carbon-carbon coupling reactions. These are extremely important reactions in organic chemistry because, as you can imagine, if you can couple two components that have carbons, a larger molecule is made. And most of the natural product molecules that are of medicinal benefits are sometimes pretty large. So these reactions here are very important reactions in organic chemistry. So in this presentation, we will look at the importance of coupling reactions. Next, we'll look at the type reactions involved in coupling reactions. It's not just one reaction. There are at least 5 that are involved, and we will discuss each in details, and they are oxidative addition reactions. We'll also look at transmetallation reactions. Then we'll look at ligand migratory insertion reactions and beta elimination reactions. And the last type we'll look at is the reductive elimination reactions. We will conclude by giving examples of carbon-carbon coupling reactions to make larger molecules. So let us begin. So in this presentation, we will concentrate on various transition metal complexes that are used to synthesize new carbon-carbon bonds. You may recall from your Gen Chem course that the transition metals are those in the middle of the periodic table. So we'll concentrate on those for this type synthesis. Shown below, however, is one example. And this is the example of palladium, and it's bonded to ligands. You may recall from Gen Chem that your transition metals are typically bonded to ligands. Here, this is the phosphorus, P, and of course, pH here means phenyl. So we have 3 phenyl that's bonded to the phosphorus. So this ligand here is known as the triphenylphosphine ligand. So here we have palladium that's bonded to 1, 2, 3, and 4 triphenylphosphine ligands. Here's another example. Palladium again bonded in this case to 2 triphenylphosphine, an alkyl group here, carbon-containing alkyl group, and over here a chlorine. So the transition metals are coordinated to different complexes, but the main aspect here is the transition metal that's used for these type reactions. So let us look at the importance of this type chemistry. As we know, a carbon-carbon bond is a very tricky bond to make in organic chemistry based on the reactions that we have done before. Because typically to make a bond, we would create a nucleophile, and then we create an electrophile, which is partially positive, and based on these opposite charges, there is a reaction to make a new bond, the nucleophile attacking the electrophile. But since carbon here, there are of equal electronegativities, it's hard to create a new bond based on the reactions that we have done before. So let's look at these here. So here is a phenyl group, and here is another group over here. So we can make this new bond here by bonding this carbon to that carbon, making a larger molecule. Here's another one. We can have this component here, right here, and we can have this component here, and using the type chemistry that we'll discuss in this chapter, we can now make this bond here to make a larger molecule. Same here. Here is one component, and here is another component, and using the type chemistry that will be discussed here, we'll show you how to make this bond here. So we have a much larger molecule as shown here. Let's show you the practical importance, or an example of the practical importance of this type reaction. This compound here, methoxycinnamate, is used in sunblock lotions. As you can see here, some examples here, and actually in chapstick for the sunblock. The main ingredient here is shown here. So this is the structure. You can see it's a pretty large molecule. But in industry, the way this is made is by making this bond right here. So by having this portion and this portion here, which we can make easily, using the reactions of this chapter, this bond here can be made, and making this very important compound which are used in sunblock. One thing I want to point out, however, that these reactions here primarily involve sp2 carbons. So here's an sp2 carbon that's bonded to another sp2 carbon. So that makes it extremely useful, because now we can bond two sp2 carbons of two fragments to make a larger molecule. Let us look at the type reactions. So there are a series of reactions that are involved in the carbon-carbon coupling reaction. So let's go through each. And you will see that as we're going through them, they're not new type reactions to us. The name may be new, but they are reactions that we are familiar with. The first is oxidative addition. We've seen this type reaction before when we make the Grignard reagent. So here is an example of an organohalide. 1-chloropropane, magnesium, oxidative state of 0, which is metallic magnesium. In the presence of ether, mix this up and have the reaction going. Magnesium here is actually inserted in this carbon halogen bond to make here this special Grignard reagent. What happens is that the oxidation state of magnesium changes from 0 to +2. So that's why it's called an oxidative addition. So that's one example. Here's another example here. So here's our palladium that you'll see quite a bit in this chapter. And this time it's coordinated to 2 ligands, triphenylphosphine ligands. Here is a phenyl that's bonded to a halogen. So this could be your typical benzene ring here and bonded to an iodine, for example. So this is this metal here inserting into that bond as you've seen here. So here's that pH right here, phenyl. Here's the X here, and this group here is now inserted into that bond. That's why it's called an oxidative addition, Notice again the oxidation state changes from 0 to +2. That becomes very important in terms of regenerating the catalyst later on when we start looking at the reactions. Let's look at another type reaction, the second type reaction, and this is called the transmetallation. As the name implies, trans, across, and metallations, across metal. This one we have also seen before because we have looked at the Gilman reagent, which is basically this, R2CuLi, but it's made from an organolithium, as shown here, reacting with copper bromide. So what we'll do is we'll transmetallate, we'll take this methyl group and put it onto our copper. So here it is, onto our copper. So we have now taken the alkyl group from lithium and transformed it and transfer it to copper. Transmetallation. Here's another example. Here's PD that has the R group, and here's zinc that has R2 and a second R group, another R group or different R group on it. When the reaction is done, this R group here goes to the palladium, as you can see, here it is, and of course we have zinc as the inorganic product. But the bottom line is transmetallation involves taking one R group from one metal and transfer it to another compound which has a different metal. Transmetallation. A third type of reaction that's needed for the carbon-carbon coupling is called the Ligand Migratory Insertion. As the name implies, it's going to be an insertion in a bond. So let's see what that looks like. Here's a classic example. Now we have palladium, which has been inserted into a bond because it's palladium 2+. And here we have an alkene, which I have in red. The bottom line is, after the reaction is done, this is inserted into this bond right here. Here's a phenyl. When it's done, here's a phenyl that's now bonded right here. And here is the palladium right here that's bonded right here. So it's a 1,2 insertion. You can imagine why it's called a 1,2 because we have carbons 1 and carbon 2. So it's a 1,2 insertion, migratory insertion. That's a very important reaction that's used as a part of this carbon-carbon coupling series of reactions. Let us look at the fourth type. The fourth type here is the beta elimination. It's actually the opposite of the migratory insertion, the reverse. So let's see what that looks like. So now that we have created the migratory insertion from the previous slide, what happens next is there's a beta elimination. So this hydrogen comes here with its electrons, so all of this migrates to the palladium, and these electrons here break off to form the double bond. Notice here we have an sp2 carbon and an sp2 carbon. So that's essentially how these reactions work. It's called a beta elimination. As you can imagine, the beta is the second letter of the Greek alphabet, so it's also called a 1,2 elimination, where we have a hydrogen or a group. In this case, it's a hydrogen with its electrons, or the hydride migrates to the 2 position here, and then these electrons swing in to form a product that's eliminated from the complex here, so we have two products. The last type is called the reductive elimination. You may recall that the palladium now is PD2+. We need to get it to PD0 to act as a catalyst so we can recycle it. So that's one of the main advantages of these reactions, is that the palladium, being extremely expensive, is recycled once the reaction is done. So the way this is done, a strong base or a base abstracts this as a proton to form BH+, and then these electrons come onto palladium, and this leaves. Palladium goes from 2+ to palladium 0, which is the catalyst. Why? Because we have 2 electrons here. You may recall that reduction is a supply of electrons. So if we are supplying electrons to palladium, it goes from PD2+ to PD0, which is, of course, our catalyst. So it can be used again. You will recall that this is the compound that we actually started with the oxidative addition. Here's another example, nickel. And of course we can have this migrate over to here, and these electrons here come in for the reductive elimination to regenerate nickel 0, which is a catalyst, because this is nickel 2+. In this lecture, however, we'll concentrate on palladium as a catalyst. So let us look at some reactions here. Let us apply these reactions to the synthesis of new carbon-carbon bonds. Let's look at the first reaction, or one reaction. This reaction is called the Heck reaction, named after a famous chemist, Frederick Heck, and is known for the discovery of this type reaction, one of the chemists. As we'll see, there are actually 3. So here we have our phenyl iodide. Here we have our double bond right here. Here's our catalyst. Here's our base. Here is another ligand. So you mix them all up and carry out the reaction. What you'll get here is this sp2 carbon right here. Let me write it as sp2, is coupled to this sp2 carbon right here. And here's that new bond right here, and here of course is the product. Okay, you may be asking, is it possible to couple right here? And yes, it is, but that's a minor product. This is the major product that we have here. So the reactions that are involved, as we'll see on the next slide, once these are mixed, will be the oxidative addition, the migratory insertion, the beta hydride elimination, and the reductive elimination. Let's see how that works. So here's the catalytic cycle. So let's see if we can work our way through this. We start with the catalyst, palladium. Of course, the ligands here could be the triphenylphosphine. Once you mix them, the first reaction that will occur is the oxidative addition, where this catalyst inserts right in here, as we have seen right here. So here's the palladium that's inserted right in here. So that's an oxidative addition. The next is a migratory insertion, where we now introduce our alkene. Here it is in red. It's going to insert right in here. As you've seen, here it is. So this is a migratory insertion. The cycle is still not finished. It keeps going. Then we have a beta hydride elimination. You may recall this is an elimination that gives the catalyst in the PD2 state and the organic product. This is, let me write it here, this is PD2 plus. PD2 plus, right here. So this is now a reductive elimination where the base pulls off this hydrogen as a proton. These electrons come in. We have a good leaving group here that leaves as I minus, and we have regenerated our catalyst. So it's just a matter of isolating it, and it's ready again for another cycle of reaction to make a compound similar to this one. So that's the real benefit of this carbon-carbon coupling type reaction. This type reaction using palladium, and this reaction cycle is known as the Heck reaction. Let's look at another one. This is called the Suzuki reaction, named after a famous Japanese chemist. This reaction uses organoboranes and palladium. As you can see here, here is the sp2 bond to a leaving group, such as in this case a bromide, but it could be an iodide. But the main difference here is the organoborane, borane that's used here. So when the reaction is done, this sp2 carbon here is coupled to this sp2 carbon to make this new bond here. The palladium is used here. Here is our base, here's our base, and so on. So of course the palladium here is palladium 0. And when the reaction is done, it's regenerated. So the type reactions that are involved here, as we'll see in the next slide, will be our oxidative addition, transmetallation, different type, and reductive elimination. Notice here that the beta elimination is not a part of this cycle. Let's see what the cycle looks like. Here it is for the Suzuki carbon-carbon coupling reaction. Again, we start with palladium 0. That's the catalyst, the transition metal catalyst. The first reaction here is the oxidative addition. Same RX, or the phenyl bromide or iodide. So that's inserted into this bond, just as before. Same type reaction. So it's inserted right into this bond here. Next, this is a transmetallation. So now we introduce another R group here from this borane. So this R group here is now transferred to the palladium, and here it is. So that's your typical transmetallation. So this R group comes from this reagent and shown here. As you can imagine, the next reaction here is a reductive elimination, where this group comes onto this one and it leaves as a product, and then we have here our catalyst that's regenerated. That's called the Suzuki carbon-carbon coupling reaction. Okay, same ultimate goal of bonding here an sp2 carbon to another sp2 carbon, or making a new carbon-carbon bond. The last reaction that we look at is the Negishi reaction, named again after a Japanese chemist. And by the way, he shared the Nobel Prize in chemistry in 2010 with Heck and Suzuki for the discovery of these reactions in which palladium catalyst is used for cross-coupling to make new carbon-carbon bonds. Here is an example of the Negishi reaction. This starts out with a zinc, so you can imagine here it's going to be a transmetallation at some point, and an alkyl or a phenyl bromide or chloride or good leaving group. Here it's a chloride, and here is the palladium again. Mix these together. What you have is a new bond here, sp2 bonded to an sp2, a new bond, and this is the product. By the way, this type product here is very important. It's anti-protozoal activity, or it has anti-protozoal activity used against infection. So this is a way of making a larger molecule from two smaller molecules here. So you can see the importance in the pharmaceutical industry. The reactions that are involved in going from reactants to product are oxidative addition, transmetallation, as you can imagine, because here's a zinc that's not in the product, and a reductive elimination. So let's see what the cycle looks like. So this is the cycle for the Negishi reaction. Start out again with palladium. Notice they all start with palladium because they got the Nobel Prize in chemistry for the use of palladium to make new carbon-carbon bonds. The first reaction, as you can imagine, is an oxidative addition. Right here again, same type reaction as we have seen to form this type complex. Notice this is now PD2+. Then we introduce the second alkyl group as the zinc complex. Okay, that can be made easily in the lab from the alkyl halide. So here's the alkyl zinc complex. A transmetallation puts R2 onto this palladium. As you can imagine, a reductive elimination gives our product with the new bond here, and of course regenerates the catalyst, which is now ready for another cycle. So I hope you can appreciate the chemistry here, because using a very expensive metal, palladium, as a catalyst, which means that it's recycled, and the bottom line is it's used to make very important compounds in the pharmaceutical and medicinal chemistry. So let us just apply this knowledge before we conclude. So a typical question would be like this, is to predict the product and the reactants for these reactions that look like this. So here we have two reactants here, and we're asked to predict the product. In the second case, we have the product, and we're asked to predict the two reactants. So just imagine you're working in a pharmaceutical lab, and you have to make a larger molecule for some reason. Again, the aspect that's important for us here in organic chemistry is, did we understand the chemistry that we just discussed? And number two, can we apply that knowledge to solving problems? So here's a problem. We have two reactants to predict the product. So what we need to do is to come up with a way of applying that. So we have to observe and analyze each reactant carefully and determine which bonds will come together, which carbons will come together. As you can imagine, this carbon here, the sp2, will be bonded to this carbon here to make this molecule over here. So again, that's one aspect of this course, is to learn how to apply that scientific analysis, observation, and of course the application to solve a problem. In the second one, we have the product, but we need to identify here are the sp2 carbons. So we can make either this bond here or this bond here, right? So it's just a matter of making a halide and the alkene as the other reactant. So let's look at the next slide and see what are possible answers. Now you can see why I put possible answers in my answer key, because I want you guys to think of alternate ways of solving problems. That's what scientists do. So if we react this molecule with this molecule, as we mentioned, here would be the point of in reaction to make a new bond, and here is that new bond, and here is that molecule. Here's this molecule here, and as we pointed out, here's an sp2 carbon, and here's an sp2 carbon, so we can make that bond, which means that we need this with the leaving group, and we need this with the alkene sp2 carbon, in of course the presence of our catalyst to make this larger molecule here. So once again, I hope you have appreciated some of the chemistry here, or the importance of this chemistry. These three chemists actually got the Nobel Prize for the use of palladium to make new carbon-carbon bonds. This is the end of chapter 13. Not too many new material introduced here, but very important information. So, like I've always concluded, just wanted to remind you that as chemists, especially organic chemists, we're here not only to learn the facts and the content, but equally how. Notice the key word here is how to apply that knowledge and content to solving problems. That process of becoming problem solvers is an important aspect of your scientific development. So continue to study hard, and I will post additional information on D2L.